We have in the previous section mentioned that the events that we are detecting are trues, randoms, and scattered events, and for the trues we have to apply attenuation correction. So let's assume we have a situation where we've dealt with the scattered events, we've dealt with the random events, but still for the true coincidences we have to consider the fact that they are not detected at 100% because some of them are being absorbed in the body. So let's look at the situation here schematically. We have our subject here, the patient, as an oval. We have a generation of a annihilation photon pair here at this point. We'll consider the direction of the photons. One photon travels a distance x through the body and the other photon travels a distance d minus x. So the total path that the photon pair travels through the body is the length is given by d. We'll now say at this point we have a tissue radioactivity of C for tissue radioactivity, T for tissue, star to indicate its radioactivity as a function of position x here. So x is our variable. Now what is the probability that the signal arrives in detector 1? The probability is given by the signal that we detect divided by the tissue radioactivity plus a few corrections, but for all the photons that go in this direction, we're only considering those. Only those that go in this direction. The photons that we detect is given by the tissue radioactivity times the attenuation. That's the signal that we get, so the probability of detecting the signal is equals to e to the minus mu times the distance traveled. The same thing applies here for this position. For this detector, the probability is given by e to the minus mu x, x being the distance from this place to the edge of the tissue. Same consideration. So if we now look at the attenuation, how do we calculate the attenuation? The attenuation is essentially the probability that we see the photon pair. So let's assume that half of the photons that go into the direction of detector 1 are being eliminated. So we only see half of the annihilation photon pairs of the coincidence events. Now let's assume in the other direction we also only see half of the photons. So for those photons that arrive here at detector 1, those half out of 150, the other photon, half of them are being eliminated. So in the end result, we have only 25 photons that we count if the total is 100. So only 50 arrive at detector 1. So we can only have 50 simultaneous events, and of the 50, half of them are being absorbed here, so we end up with 25. Or in other words, the probability of detecting the photon pair is given by the multiplication of the two probabilities of detecting each of the photons. So this is the probability is equals to e to the minus mu x times e to the minus mu d minus x. And so we can simplify that. We have the signal now is the probability of the photon pair times the tissue radioactivity. And so this gives rise to an attenuation. We have the signal is equals to the tissue radioactivity at this position times e to the minus mu d. If you take this term here, you'll see rapidly that this is equals to minus mu d. And this is quite similar to this correction to the geometric average that I introduced last week for SPECT scanning in lesson 5. So what this means is essentially for doing the attenuation, estimating the attenuation, we just need to know the dimension of the object along our radon transform along our orientation, and from that we can calculate the attenuation. Be aware that here in this situation we've assumed uniform attenuation. In reality, the situation is slightly more complicated. Here is a uncorrected PET scan of a subject. Here is the cut through the torso. We can see the nose here, the spine, and here's the coronal. Here we have the bladder. Here we have the brain. The arms are up here. This is the uncorrected scan, and here is the scan corrected. And you can see certainly if we correct for the attenuation, if we take the sinogram and correct it for attenuation, the images are much more crisper and clearer in allowing us to discern the uptake of the radio tracers. So attenuation correction is important in producing a faithful representation of tissue radioactivity in the body. So what are the steps in attenuation correction that we need to do for PET? Let's look at the mass attenuation coefficient in soft tissue. This is roughly 0.1 centimeter squared per gram for the 510 kiloelectron volt photons. Now, does this give us an intuitive feel for what this means? Is it quantitatively important? We'd have to do some calculation. So the more easier way to assess this is to look at the half-value layer of these photons in soft tissue. The half-value layer, as you might remember, is 0.7 divided by mu, the linear attenuation coefficient. And so it turns out that for photons in soft tissue, the half-value layer is roughly 7 centimeters. So that is not a very long distance. We have to consider that the entire path of the photon pair through the tissue is taken into consideration. It's the distance d that we had on the previous slide. So it is longer than for a single photon. But we also have to consider that the lines of response, lines of incidence have different attenuations depending on how big we are. If we were perfectly cylindrical objects, if we were imaging perfectly cylindrical objects, it wouldn't matter as much. So what are we doing in practice? And for this example, I'll assume a spatially uniform attenuation coefficient. I have my subject here that is oval, and one uses, for example, can use a cesium source in this illustration. The cesium source has a photon energy of 660 kiloelectron volt. Now, why is this good enough for estimating the attenuation at 510 kiloelectron volt? Remember this, we have, at these energies, we have the Compton effect that dominates, and the linear attenuation coefficient for Compton is essentially proportional to the electron density, and that varies very slowly with the photon energy at these high energies. So it is a good approximation of what is going on. So we just take the source, we rotate it, and we have the detector on the opposite side, and we will measure the intensity as a function of the angle phi. We have seen the thing rotate. Now this is not good enough. We have to compare that to the blank scan. The blank scan means we will remove the subject. So here's the subject removed. We repeat the same scan, so we measure the intensity of the source as it is being detected. And then we divide the two intensities, and what we are obtaining is e to the minus mu d, and d here, this is important, is a function of the projection angle that we have. So as we rotate around for an object that is, for example, elliptical, we have different attenuations to consider. So this basically means we will produce a correction for each radon transform, for each orientation. This example that you have here on the screen is for a homogeneous linear attenuation coefficient here. Mu doesn't vary. For situations that are more complex, as in real life, we would actually have to integrate the linear attenuation coefficient along the perpendicular to the projection, and this is nothing but the measurement of the expression that we have for a CT scan. So if we look at the PET imaging of the body, let's look here at this subject that's in the PET scanner. And I want you to think a little bit here. What is being scanned here? What organ? Well, it's not the head. The head is outside the scanner. We are outside the detector ring, is here, so it's not the head. It's not the prostate or the lower abdomen. It is actually at the level of the heart. It's a heart scan. So second question, why is the subject putting his arms behind the head? Because they like to be relaxed, or because they were being told so? Well, look on the left. The half-value layer for positron photons is 7 centimeters. This means if you take an average thick arm, like mine here, roughly, let's say it's 7 centimeters, and I put it on the side, and I measure the radon transform in this direction, the projection. Putting my arms down means that I increase the average path length by 14 centimeters. That is, I only detect 25% of the photons. So for a hard scan, I will measure in this direction a substantially reduced intensity. So if we have the arms along the side for a cardiac scan, we have a lot of attenuation because we have the additional attenuation of the arms to consider. And so for a heart scan, we put the arms up and we scan around here, and so the arms don't enter into play. Conversely, if we do a brain scan, we're not going to put the arms here because that we will introduce again for a substantial fraction of the projections that we measure. We will lose substantial intensity, and that is not good. We want to have the best intensity, so we do not expose our subject to a higher radiation dose than necessary. I mentioned early on that the PET-CT scanner is the industry standard. You can no longer buy a PET scanner that is standalone. You buy them together with a CT scanner. We have on the previous slide seen that the attenuation correction uses expressions or measurements that are akin to what is being done in a CT scanner. And so I want to explain here how this can be done. We have plotted here the mass attenuation coefficient on the vertical axis here versus the photon energy on the horizontal axis. And this is roughly the change in linear attenuation or mass attenuation coefficient for soft tissue. And in red and in green, we have the same for bone. The photon energies that are used for CT scanning are typically between 30-40 kiloelectron volts to 120 kiloelectron volts. And so we obtain, at these energies, we obtain a CT scan of the body, which is depicted here. So this is roughly a scan at roughly 17 kiloelectron volts that's been done here. Now, what one can do is, given that we can easily identify bone in a CT scan and soft tissue, we can extrapolate what the image would look like, and we get then the CT scan at a supposed photon energy for 510 kiloelectron volts. So this is done by extrapolation. A bit more sophisticated, here's a CT scan. You can see the lungs in white, no attenuation. You see the head here, you see the rib cage, a lot of attenuation. And now based on the absorption, since the bones have a lot of electrons, they have a lot of calcium, we can actually identify the areas, calcium-rich areas. This is the such segmented image for bone and for soft tissue. And since we have in green the extrapolation of the mass attenuation coefficient and in red the mass attenuation coefficient for soft tissue, we have these two images. One can calculate a synthetic image taking into account the effect of slightly differential effect of bone, and this gives us now the distribution of the linear attenuation coefficient at 510 kiloelectron volt. So this measured at low energy, segmented into bone and soft tissue, recomposed with the measured mass attenuation coefficient for 510 kiloelectron volts. And this, in the end, will give us the justification for combining here a CT scan with a PET scan. So this is a CT scan of the abdomen. Here's the heart, black is the lungs. We have the PET scan of the same area in grayscale. And now for the fusion of the two images, the PET scan is color-coded. It's lower resolution than a CT scan, superimposed on the high resolution CT scan. And now one can easily see with the warm colors delineating high activity in the tissue where the high activity of the PET tracer uptake is. So PET-CT is actually not one modality, although in theory one can think of doing it this way. It is actually in reality two scanners. We have up front, the patient first sees the CT scanner and behind it the PET scanner, and they're put into a single package with a nice little cover. So we have the patient bed, we'll put the subject on here, and the subject first undergoes for a few seconds a CT scan. Once that is done, the patient table is moved forward, and then we take another 10 minutes for the PET scan to measure the uptake of the positron emitter in the body of this subject. So it is PET-CT, two scanners in one package. That puts the two techniques together.